Okay, so thank you for the kind introduction, and I want to thank the organizers for inviting me to Singapore, and particularly for the kind hospitality I felt here. So, as mentioned, I want to talk about dynamical signatures of quantum spin liquids. So, quantum spin liquids are actually an example for topological phases that emerge due to strong interactions in quantum spin systems. And as we already heard in previous talks, these kind of exotic phases are theoretically characterized in terms of emergent gauge fields and their entanglement. But these are actually hard to detect in actual experiments. So the question is, like, if someone has synthesized a new material, how to actually detect if or what kind of spin liquid we might have realized. And in my talk, I actually want to discuss then two approaches, like one, like by starting from some simple model system and then making some analytical predictions. And the second part, I want to introduce some new numerical tool that we can use to kind of simulate the dynamics of such systems. So just start with some brief introduction. So we actually know by now that there are kind of a variety of different exotic phases. All of them we would call topological phases, although these topological phases can be very different in nature. I mean, some of them require certain symmetries, like topological insulators are only topological as long as we have certain symmetries, while others are much more robust, like the quantum Hall effects. And moreover, some of these phases can occur just in a simple single particle picture, such as the integer quantum Hall effect and topological insulators, while others are sort of emergent topological phases where basically the interesting stuff is only happening because the particles would strongly interact. And among this category are quantum spin liquids. So here the interactions between particles or the will be actually quite important, and the interesting topology arises here as an interplay between quantum fluctuations and strong interactions. And kind of characterizing and fascinating features that these phases exhibit are fractionalization. So like in the fractional quantum Hall effect, we can have particles that carry fractional quantum numbers. And moreover, these fractional excitations can have fractional statistics, or like anyonic statistics, which means that the emergent particles might neither be bosons nor fermions, or moreover, we can have emergent fermions in simple spin systems. And the characterizing property here, as we heard, for example, by Nicolas, is the entanglement. So we can have interesting pattern in the entanglement spectra, or we can have some non-local entanglement that we cannot remove by any local unitary operations. So again, these are mostly rather kind of theoretical properties of these phases. And the question is, like, what are now the resulting features that we can detect in a concrete experiment? Right? So this is now what I want to do. I want to basically bridge some of the theoretical understanding that we have of such phases to experiments that can, in principle, be done in a laboratory. And what I want to propose is to actually look at dynamical properties of these phases. In particular, I want to look at the dynamical spin structure factor. Right? Basically looking at the probability of finding excitations with lattice momentum Q and energy omega, given here in the Lehmann representation, for example. And there's already some nice example where this was actually done quite successfully. In particular, there are certain materials that can, in a very good approximation, be described by simple kind of one-dimensional spin chains. Moreover, the physics that Duncan Haldane talked about this morning, about having spin-on excitations in one-dimensional spin 1/2 Heisenberg chains. So in this, the spin 1/2 Heisenberg chain represents a one-dimensional gapless spin liquid with fractionalized spin-on excitations. So having this in mind, one can now look at the experimental data. So here we see on the left panel the results of neutron scattering experiments, where we have here on the y-axis the energy and on the x-axis the momentum transfer. And what we see here is that there's a very broad continuum. And this broad continuum is due to the fact that a single spin flip is actually creating a pair of spinons, and then the momentum of the original kind of neutron that hits the system is then distributed among these two spinons, and then we just see the superposition of these two dispersions. And moreover, for this single kind of one-dimensional system, we actually know some exact solutions due to the beta ansatz. And while this is what Duncan Holden pointed out, there has been a lot of development on these techniques. And moreover, since a couple of years, one is actually able to calculate also dynamical correlations from the beta ansatz. And these are here now compared with the experiments. So on the left-hand side, we see the results of the experiments. On the right-hand side, the theory. And one sees that they match nicely. At least they match nicely for the higher energy part. So, and taking these two together, it's very satisfying. So because first, one sees these broad features that we get from these spinon excitations. And moreover, it can be just, at least at a qualitative level, be nicely compared to some simple theoretical model, and they match quite nicely. So, and now this is a success story for systems that are basically one-dimensional. And now one just tries to do kind of similar things for two-dimensional systems. So, and there have been now several proposals for spin-liquid materials. And well, one case, or like one kind of place to look for spin liquids are so-called frustrated lattices. So for example, geometrically frustrated lattices, where the lattice geometry prohibits certain kind of obvious orders, like for example, a Néel state. And there are materials that realize these kind of interesting lattice structures. So and then one of them, for example, is Herbert-Smithite. And then there are experiments, like neutron scattering experiments done on these materials. And what is found in several of these kind of candidate materials is that there's a broad structure. So there are no magnon peaks and no sharp features. And this is generically interpreted as some indication for the fact that we do have some spin liquid. But the thing is that what do we actually see? And it would be nicer to have some more qualitative or some more kind of quantitative things to look for, except saying that we do not see magnons or single magnons. So and this is now exactly what I want to discuss. So in the first part of my talk, I want to discuss some simple model. So basically, I want to just to think that, well, let us assume that we have a gapped topological spin liquid for which I know that the emergent excitations are anyons of a specific type. And I want to ask the question, based on this kind of simple assumption, what can we actually, can we make some universal or some generic predictions about the dynamical spin structure factor? And in the second part, I want to introduce some numerical tool to obtain the dynamical properties for two-dimensional quantum spin systems. And in fact, this is based on a method that Nicola already briefly introduced for ground state properties, namely the density matrix normalization group. And I want to show that we can use the same method to actually also get dynamical response functions. So let me now start talking about the first part. In the first part, where the main driving force was Siddharth Murampudi, who was a PhD student in my group back in Dresden, and he just moved recently to Boston, and also involving Ari Turner and Frank Wilczek. So let me first set up the stage for this problem. So here I want to make the assumption that we're actually now dealing with a topological kind of quantum, like a gapped topological state of matter. So and here I can think of the ground state as being a superposition of some sort of loops. To be more concrete, if you have some resonating valence bond states, these loops could be made of alternating having a dimer not having it, or having a singlet not having a singlet. In the kind of toy models like the toric code, these loops could maybe be made of up spins, while not having loop means we're having a down spins, etc. So anyway, the ground state I want to think of as just being a superposition of states where we have closed loops. And now if we create an excitation by, for example, shining a neutron onto this ground state, I want to assume that the excitation will actually break up one of these loops, and we have now a string with two open ends. And at these open ends, we actually have now anyonic excitations. So in particular, even though we started from a simple system of localized spin particles, say, then these excitations become very kind of non-local particles in the sense that even if I just pull them very far away from each other, I exchange them, due to these strings and loops, they actually get this statistical interaction. Namely, if I exchange them, I assume that they pick up a phase of e to the I alpha. Good. So this is now the underlying assumption, and I assume that all this happens only above a certain energy gap. So why am I interested in looking at these exotic particles? Namely, these kind of particles say something about the underlying topological phase. So if we have a topologically ordered phase, we can actually characterize this topological phase by the set of different kind of anyons we can have. And this can be relatively simple in certain. For example, there are these chiral spin liquids, and chiral spin liquids, they have two different types of kind of non-trivial anyons, and these would be semions that have a statistical angle of plus or minus pi half. And other topological orders can have more exotic particles or different sets of these quasi-particles, etc. But this would be now a simple example. So, and now we just going back to some very old works by Wigner. And in particular, what he found is that the behavior near cross-sections, the cross-section near thresholds, only depends on long-range interaction. So he basically looked at the pair production of charged particles which interact maybe via one of our interactions. But here we have now a system where we again have a pair creation, but these are now basically particles where we first of all assume that they only interact via this statistical interaction. So, and then we can actually just sit down and just simply solve a two-anyon problem, which is basically a simple physics problem where we just use separation of variables, and then we just obtain the wave function. And then, of course, as we know, there will be a stark difference between bosons and the other particles. In particular, bosons like to be close to each other, while the other particles don't really like to sit on top of each other. And we see also like the way how basically the wave function decays to zero depends on the statistical angle. Moreover, since we do have the exact solution for this two-anyon problem, we can then plug it into the expression for the spectral function. So this is just, again, the Lehmann representation. We have solved this problem exactly, so we can just plug in all the excited states and evaluate the sum. And what we find is that the S of Q and omega is just given by the Bessel function about the gap. So, and if we just expanded this function to lowest order, what we find is now the following. So here what I plot is now the spectral density or the spectral weight at a given momenta. So here I just choose Q equals to 0. And now I look at the spectral weight above the gap. Right? So below the gap, we don't have any excitations because there are no excitations that we could scatter into. But above the gap, we do have a certain density. And for bosons, it would be constant. So this alpha would be 0. For semions, we actually find a square root behavior. So the alpha is 1/2. And for fermions, it's linear. So this alpha here is 1. So what we find then is, like, at least if we start from a system of non-interacting anyons, that the near threshold, like right above the onset, that the spectral weight scales depending on the statistical angle, right? So alpha here is now basically the statistical angle that I showed before divided by pi. So this was now the answer for just a system of non-interacting anyons. But generically, we will have some interactions. And moreover, if we have this angle alpha larger than 0, meaning that we are not looking at bosons, then the short-range repulsive interactions would not affect the low-energy behavior, which we can show because of the fact that basically the short-distance physics is only affecting the high-energy features. And if we have bosons, or moreover, if the statistical angle is 0, then we actually get corrections. And instead of finding just a constant, we will find this inverse log squared. So this is now done just for a simple kind of continuum model. And then we just want to see what's happening at a lattice model. So we do some numerical simulations. In particular, we just take a square lattice and we put two anyons on this square lattice, and we calculate the dynamical structure factor for different interactions between these anyons. In particular, we have repulsive interactions between nearest and next nearest neighbors. And what we see here, so here we plot again S of q equals to 0 and omega as function for different omegas above the gap. And we see that in the low energy part, it indeed appears to be linear. And if you plot it on a log-log plot, we actually find that it is nicely linear. And moreover, it's linear for all sorts of interactions. While the high energy part is then affected by the interaction. It looks non-universal. And now we can do the same thing for semions, bosons, and hardcore bosons, etc. And well, from this plot, you cannot really read off much, but if we just look closer at the data, it actually reflects what we would expect. And we can now also use similar arguments for certain cases where we assume that the like a spin flip, say, would create not 2, but maybe 3 different anyons. 3 anyons obviously all of the same type. So this is all I want to say about this, the first part. And mainly we have looked at this problem for a very simple angle, where we just start from non-interacting anyons, and we find some features that appear to be universal and not depend on short-range interactions. It becomes different when we include long-range interactions. For example, Coulomb interactions between these anyons would destroy this. For the scaling, there's some, so if we have just some scaling with, or the interaction with 1 over r to the power, say, beta, then the critical dimension would be beta equals to 2. And moreover, if we have quantum Hall states where we have a background flux, that would also quench the kinetic energy and again make this destroy this story. But there's a certain range of models where we actually expect this to work, and we are now trying to be more careful of other effects that could happen. So this was the first part, where we just started from a simple kind of picture of what's happening. And in the second part, actually, I want to be a bit more concrete, and I want to, because the question might be, if we have now a particular model Hamiltonian where we believe that this describes some interesting physics, how can we actually compare this now to experiments? And here I want to discuss the work done is mainly by Matthias Gohlke, who is currently a PhD student in Dresden, and Ruben Veresen, who is a PhD student working with me in Munich right now, and Roderick Mössner. So in the concrete model that I want to look at this moment is the Kitaev model, well, like one of the Kitaev models, and this is a Kitaev model on a honeycomb lattice. So that might be familiar to many of you, but I just want to briefly review the terms in the Hamiltonian. In particular, we have a simple spin 1/2 system. So we just have spins, say, plus or minus 1 sitting on each side. And they have a highly anisotropic interaction. So on these purple bonds, there's only sigma x interaction. On the green bonds, there's only y, and the blue bonds, only zz interaction. So this is basically a quantum compass model. And it was Kitaev who then showed that this model can actually be solved exactly. And it is actually quite an exciting model, as it has gapless excitations that are Majorana fermions. So these are some emergent fermions in this spin systems. And we have static and gapped flux excitation. So we can, like, for each of these plaquettes, we can define an operator or like a Z2 operator, and the flux is conserved. And in fact, the fact that these fluxes are gapped makes the system exactly solvable. So, and that at the first glance looked at like an extremely theoretical model, but it then was argued by Giacchelli and Calloin later on that in fact this might be some this model in a certain approximation describes the physics in iridates, where actually because of strong spin-orbit coupling, they actually exist very anisotropic couplings. And more recently, it has been argued that another material, alpha ruthenium chloride, might also be described by this physics that could occur here. And the minimal model basically to describe these systems would be the so-called Kitaev-Heisenberg model. So here we have then some interplay between the strongly anisotropic Kitaev term plus an isotropic Heisenberg interaction between these spins. And the model that we look at is now basically parametrizing these two terms, and then we just explore the phase diagram. I mean, note that in these materials, there will be many other terms that will be relevant, but just to get a first glance on what's happening, we actually now look at the simple Kitaev-Heisenberg model. And as I already pointed out, in order to kind of understand the physics of these systems, except at kind of fine-tuned, exactly solvable points, we're actually dealing with a full-blown quantum many-body problems, and that means that we need quite some powerful tools to solve these problems. And as Nicola already pointed out, one of the tools is to use exact diagonalization, basically by just really construct the many-body Hamiltonian as a huge matrix and then diagonalize it. But with this, we can do maybe the order of 20 or no, maybe of 30 or so spin 1/2s. And what I want to propose here is to use the density matrix, or in fact this infinite system density matrix method. And again, as Nicola already pointed out, the underlying idea is that the ground states of local Hamiltonians are very special states, and in fact we can just focus on a small corner of a Hilbert space, and that small corner is described by the manifold of matrix product states. So namely, the idea is that we just express the amplitude in a many-body wave function in terms of a product of these rank 3 tensors or order 3 tensors, and then once we would multiply all of these guys together, we get then the amplitude in a wave function without actually storing it. So this is now basically the manifold of states that we look at. So we can just literally see it as a variational wave function with many parameters, and the numerical tool to minimize the energy within this manifold of these MPS is the density matrix renormalization group method. And this method, as you already might kind of guess from the setup, is basically a one-dimensional method, but having kind of made some progress on the method itself and computers being now much faster than they were 30 years ago, we can now, or 25 years ago, we can now actually use this method to also tackle two-dimensional system. And the simple idea is just that we say that, well, we take our two-dimensional system, which, for example, is this honeycomb model, and we wrap it on a cylinder. And then we just map it basically to a one-dimensional system by just kind of enumerating the numbers like winding around the cylinder. And then we get basically a mapping like this, right? So this is like a 2D system. We map it to a one-dimensional snake here. And the cost that we are paying is that even though we started from a system with only nearest neighbor interactions, the resulting 1D model actually has now long-range interactions. Like here, for example, we have now interactions between site 1 and site 5. And that gets worse and longer range as we make the cylinder wider. And that comes at a large cost for the numerics, namely the numerical cost is growing exponentially with the circumference L. But again, thanks to modern computers and some advances in the technique, we can actually push it up to roughly L equals to 12 for the Kitaev model, of the Kitaev-Heisenberg model. So now we can use this method and look at the phase diagram. And again, this is now mostly due to work of Matthias Gohlke, who just implemented then this Hamiltonian into our DMRG code and explored the phase diagram. And we just parameterize the Hamiltonian by this angle alpha, so that if alpha is equals to 0, we have the pure Heisenberg model, which is in the Néel phase. And then if we just go to alpha equals to pi half, we actually at the Kitaev model. If alpha is equals to pi, then we have an Heisenberg ferromagnet, and at 3 pi half, then we actually at the ferromagnetic Kitaev point. And then in between, we see various phases and phase transitions. And here I just basically want to point out that using this DMRG method, we actually find results that resemble quite much what was found before using exact diagonalization and using tensor product states methods. So the only disagreement is that the Kitaev phase here is slightly smaller than it was from the original exact diagonalization study. And the way that we detect the phase transitions is, on the one hand, to look at discontinuities in the ground state energy density, which show kinks here, which indicates that at least using DMRG, these transitions all appear to be first order. And secondly, we look at the behavior of the entanglement entropy, basically how, say, if we just cut a cylinder into two halves, it is entangled. And we find that there's like a very different behavior of the entanglement, and also we see discontinuities in the entanglement entropy. We see that the ferromagnet, for example, is a simple product state, so at zero entanglement, and this critical spin liquid phase, namely this Kitaev spin liquid phase, actually has a rather high entanglement. Good. So this is all I want to say about the ground state phase diagram, but I want to point out one subtlety. Right? I mean, I think that this DMRG method is a very powerful tool to study these 2D systems, but we have to be quite careful. And this is now for the following reason. So we have this Kitaev spin liquid, and this Kitaev spin liquid has actually Dirac cones, or like these Majorana cones. If, however, we just put our system onto a cylinder, what we get is, like here we just see the Brillouin zone. We actually have cuts through the Brillouin zone. So we have a continuum of momenta along the long direction of the cylinder and discrete momenta along the short direction of a cylinder. So, and we already know when we fabricate carbon nanotubes that it actually matters quite a bit how we wrap the graphene on a cylinder, right? So we can either hit the Dirac cones and we get a semi-metal, or we actually wrap it on a way on a cylinder so that we do not, that these Dirac points are at not at allowed momenta, and then we actually have an insulator. And the same thing is also true for our spin liquid, or for our problem here, because if we, depending on what kind of geometry we choose, we can actually get either a gapless spin liquid or a gapped spin liquid on the cylinder. But in fact, the Kitaev model is slightly more tricky than graphene. And the reason for this is that the excitations actually can feel an emergent sort of Z2 flux that goes through this system, right? So basically, it's a topologically ordered system. So we have different topological sectors. And these sectors, in this case, are distinguished by having a Z2 flux going through this cylinder or not. Now, the excitations actually can sense this flux. So if basically we are in a zero flux sector, the particles hop once around the cylinder, we might feel periodic boundary conditions. And if we do have a Z2 flux, then the particles feel antiperiodic boundary conditions, which just shifts the momenta. So basically what I'm saying is that even if we were careful to choose the right geometry, the actual ground state using DMRG might be in the other sector. So the DMRG code would just automatically, or by itself, produce a Z2 flux. And again, we would see a gapped spin liquid. So we have to be very careful about how we initiate and how we run the DMRG code. And in fact, in a related work, we just showed that this might also have led to some wrong conclusions about the Kitaev-Heisenberg model. Namely, we find that indeed, if one is doing this very carefully, that there are indications that the Kagome spin model is actually a Dirac spin liquid. Good. So now, assuming that we just did everything right to find the ground state, we are now interested in finding the dynamical excitations. And here we use the following procedure, which has been used before to get one-dimensional spectral functions. In particular, we first find the ground state just using the standard DMRG technique in terms of a matrix product state representation, and then we just hit it with some operator, which could be, for example, Sx or S plus or Sy, whichever operator you're interested in, and then we just evolve the state. And in most cases, we are just very afraid of time-evolving states using DMRG, and this is because we say that, well, the entanglement is growing linearly as function of time, and then within a very short time, like, we are dead, in particular if we just do it for a 2D system. Here, however, we're actually starting from a ground state, and we're just creating a local excitation, And that, even after a relatively long time, creates only little entanglement, as this is actually a zero energy density perturbation to the state. But the one problem that we still remained with is like how do we do the time evolution? Because unlike simple 1D system where we say we have a Heisenberg chain where we can do a trotterization to then do the time evolution using standard methods, here we have now these long-range interactions. And these long-range interactions actually make the most of the kind of standard methods rather inefficient. And here actually we made recently some proposal for a new type of time evolution using so-called matrix product operators. This is like a technicality, but with this kind of new technique, we can actually now nicely evolve these states in time, even though we have long-range interactions. So we take this now together and just do some benchmarking. And this is now actually the neat thing about this Kitaev model. The Kitaev model has these exactly solvable points where we not only get the ground state, but we can indeed get the exact solution for the dynamical correlations. So we just do some benchmarking first. And what we are showing here in this inset is now the real-time data. So here we see on the x-axis the time, and on the y-axis we have now the correlations, or the real part of the correlations. And then we see the red line here is what we get from our numerics, where we just look at times up to 40. And the dots are now the exact solution from the Kitaev model on a cylinder. And we see that the numerical data that we get and the exact data on a cylinder agree perfectly well. And then if we just compare it to the exact solution in the 2D plane, we see after certain times it starts to deviate. And this is because at certain times, the particles actually sense that they actually live on a cylinder where one of the dimensions is compact, and then we actually get these deviations. If we then take this data and do a Fourier transform to get S of k and omega, this is what we get, and this is now comparing then the data that we get from a cylinder to the exact data on the 2D plane. And here we see that in this case, the agreement between the numerics and the exact solution is quite good. And here, in fact, we just tuned the Kitaev phase into a gapped spin liquid just by adding certain anisotropies to it. But if we go to the isotropic case where it's gapless, the data it still agrees reasonably well. In particular, we see that the qualitative features agree. And I want to stress again that the artifacts that we see here are not due to DMRG doing a bad job. It's just that the cylinder sizes create some finite size effect on what we see. So now after we are reasonably confident that the method is doing a good job, we can now go to unexplored territory. So first of all, we look actually at the simple Néel state, so where we have simply the Heisenberg model on the Heisenberg model on a honeycomb lattice. And here we show the data. So as I already pointed out, what we see is we have now a continuum momentum resolution in the long direction and discrete into the other. So we have basically cut through the Brillouin zone. And here we show data for say ky equals to 0, and or k2 equals to 0, and k1 in the first Brillouin zone, and we compare two different spin wave solutions. So we see that there is quite a deviation from second order spin wave. But if we just go to higher orders, so the first order spin wave, linear spin wave, has quite some deviations, but second order spin wave looks reasonably good in comparison. If, however, we now tune away from the Néel point, we go closer to this spin liquid phase, we actually see that certain like some continua emerge here, and these are not captured by the spin wave approximation, and they're actually due to these extra Kitaev interaction. What actually is creating these continua, whether these are some multi-magnon excitation, whether this is due to some, I don't know, whether this continuum has anything to do with what we get from the Kitaev phase, this is something that we are currently still investigating. And now we can just be more ambitious, and we can actually say that, well, let us now tune into the parameter regime, which we think is relevant for certain experiments, right? So I pointed out in the beginning that there's certain material that resemble this kind of Kitaev physics, and one of them is this alpha ruthenium chloride. And from just the ground state correlations at low temperatures, it is known that it actually has this particular zigzag order as shown here. So it's in this zigzag phase. So what we can do now is we just take our model Hamiltonian and we just tune it into this zigzag phase, and we obtain the dynamical correlation functions, which we then here directly compare to the experiments. So, and we notice certain similarities. So first of all, for low energies, we actually see hints for the ordering. So here we have the breaking of the symmetry. So here we have some Bragg peaks. And if we go to very high energies, in fact, we find this kind of incoherent blob at the gamma point. And in fact, if you look at the what we get for high energies, it exactly resembles what we get exactly at this Kitaev point. Right? So this is now for the pure Kitaev model, and it looks quite similar to what we get for this Hamiltonian, where the ground state is in the ordered phase. And this is still, at least to me, some sort of a miracle why the high energy physics in the ordered phase resembles so closely the physics of this spin liquid phase. And if you look at intermediate energies, we actually see some kind of star-like feature, which is also seen in experiments. But again, at least I don't have a good theoretical understanding at the moment what is causing this physics at higher energies, and this is something that we are now trying to understand better by closely looking at the wave function and other correlators. And that already brings me basically to the end of what I want to say. And also point out now that we have this new method, we now just started to investigate several other properties of systems. So one of the things is that we actually want to go back to well-known problems like the Heisenberg model on the square lattice, and actually just compare to various expansions or perturbative results that we got before. And we also now try to investigate other spin liquid candidates, which we then try to compare to experiments. So let me then conclude. So first of all, I discussed some universal features that we would expect to find in gapped topological spin liquids, namely where we get some scaling of the spectral weight that depends on the exchange statistics of the anionic excitations. And the second part, I wanted to introduce the DMRG method to get the dynamics for two-dimensional quantum spin systems. Let me also conclude by thanking my collaborators. In particular, I want to thank Siddharth Murampudi, who did a very good job on the first project to do these calculations. And in particular, I want to thank then Matthias Gohlke and Ruben Veresen, who did a great job on getting these dynamical correlation functions. So thank you for your attention.
Can you go back a few slides on the DMRG results for the Kitaev model? Yeah.
Which?
The pure nail phase. Here.
Nail phase, okay, yeah. This is the nail phase with a slight
so there is a
anisotropy, yes.
And in the previous slide, this time is real time.
Yes, so here this is the real time, and and this is in terms of units of inverse k, like the coupling of the Kitaev term.
And this operator that you introduced, s plus e to the I h t s minus, the Hamiltonian is the full Hamiltonian for the time.
Wait, here,
this
like for the exactly.
No.
See. So for the exactly solvable point, the Hamiltonian that we take is only this guy here, only the anisotropic part. So.
No, when you introduced the correlation.
Of the dynamical correlations?
Yeah.
Yeah, at that case, I mean, the way that what I'm showing
right
here, it's just, here I'm just doing it for S plus, S minus, but what I'm actually showing there are the correlations between SZ, SZ. So we just kind of take the state, the ground state, we hit it with SZ at time 0 and position 0, and then we just look how these are then correlated with applying SZ again at time t and position x.
And those are real times?
This is real time, yeah.
I see. Thanks.
Test.
Thank you. Nice talk. I have a simple question. In the first part of your talk, you discussed the characteristic signature of the dynamical structure factor of the spin liquid phase.
In the first part, I'm looking at the dynamical, yes?
Yeah, and then your finding of the characteristic signature of the spin liquid can be applied to the only two-dimensional case?
Well, in the first part, I'm interested in the anionic statistics, and the anionic statistics, at least if for point-like particles, would only make sense for two-dimensional systems.
Okay, and only gapped case?
Yes, and I'm requiring a gap because otherwise there would be just zero energy excitation. So that would, for example, not apply to the Kitaev case where we actually have gapless Majorana excitations because they would actually interfere with those, and then it would not work.
Okay, and one more question. Even in the Kitaev model, you know the...
Even in the?
Kitaev honeycomb Kitaev model.
The honeycomb.
But if you apply the strong anisotropic case, we have a gapped spin liquid. So
you have a gapped spin liquid.
Yeah, in the Kitaev system, Kitaev model. So can you apply your finding in the first part of your?
Yes. So this is approximately what we did here. If you take the anisotropic case or the gap, if you take the gapped Kitaev spin liquid by having the anisotropies between x, y, and z interactions, then the model becomes perturbatively a toric code type of Hamiltonian. And for that, you have exactly this kind of picture. I mean, this is basically the kind of model that we simulated here, where we just say that we have a square lattice model, and then we just create these excitations on neighboring lattice sites, and then this would apply, yes.
Thank you.